So let's look at the application of series expansions for solving differential equations, and we will consider a first order ODE in this example. So we're going to use the idea of truncated series illustrated in the context of first order nonlinear ODE. And so this is the most general first order nonlinear ODE. And what we're going to do is we're going to consider cases where this right hand side does not depend on time. So time factor is going to be eliminated from consideration. So let's cross that out. And so to illustrate this approach, we will begin by first finding the equilibrium solution. Equilibrium solution, remember, y equals ye is an equilibrium solution if the rate of change of the solution vanishes, meaning it has reached equilibrium, it does not want to change the value of the solution anymore, and therefore substituting this in the differential equation gives us this relation that f of evaluated at the equilibrium solution must be equal to 0. And so one important question that we want to understand is the nature of the solution when y is close to this equilibrium solution. So the question is, if the initial condition is such that y is close to the equilibrium solution, then would it stay close to the equilibrium? Would it come closer to the equilibrium solution? Or would it run further away from this equilibrium solution? And so that's one qualitative question that we can answer using the series expansion. To address this, let's consider that the solution y is close to ye, and therefore we explicitly define a new variable z, which measures the difference between y from ye. So y minus ye is defined as a new dependent variable z. And if we simply differentiate this with time, since ye is an equilibrium solution, it does not vary in time, taking derivative of both sides will give us that the derivative of z in time is equal to the derivative of y in time. And this is something that is prescribed by the differential equation, and therefore we have the differential equation rewritten in terms of z. So z dot equals f of y, but y is ye plus z. You can just rearrange from here. Y would be z plus ye, and so we substituted that. And so now we have this right hand side evaluated at ye plus z. And so since z is close to ye, we can say that the function at a nearby location close to ye can be found using a Taylor series expansion of f near ye. And so this is the Taylor series expansion. First term, a function is evaluated at ye. The derivative of f with respect to y evaluated at ye times the displacement from the equilibrium solution, z. Second derivative, z square, and higher order terms, and you can keep more terms if you want to. We are indicating that these terms are of order z cube, and in what we're going to do further is we're going to truncate the series. We're going to drop any further terms. So if we take this truncated expansion and we're going to label the terms that are appearing as coefficients, these are numbers or they're constants. Note that f of ye is actually equal to 0 because ye is the equilibrium solution, so this will drop out. And df dy at ye we're going to simply call by this symbol fe prime, which is a number which we can calculate for a given problem. And likewise this is another number, and we will call it fe double prime. So we can rewrite this equation in this simple form. Z dot equals fe dash, a number, times z, plus 1/2 fe double dash, another number, times z square. And let's say we know the initial condition for z, that z at time t equal to 0 is some number z naught. And so this is now a first order a nonlinear differential equation. It's nonlinear because we kept this second order term. If we want to consider the lowest order truncation, we can drop this, and then we would just have the linear term. This would be gone, and then we would have a linear first order differential equation, which we can always solve, and that will give us a sense of the nature of solutions. But we can do a little bit more. We can keep this term, and you will see in a second that we can actually solve this problem with this initial condition. If you think about this, this is a problem we have solved before, just of this kind. And so we'll indicate the steps that we had taken. What we can do is we can separate the variables, and we can solve this first order differential equation using partial fractions on the left hand side of the equation. And so we're not going to repeat those details here. You can look it up, or we have discussed that before, to obtain the solution in this closed form. So z over z naught, remember z naught is the initial condition, is given in terms of this explicit formula involving these coefficients. And in writing this formula, I have assumed that f e prime, the slope of the function evaluated at the equilibrium position, is not equal to 0. If it is equal to 0, then obviously this term will vanish, and we will have a leading quadratic term, and so that is also a problem that can be solved. If this term is 0, that equation can also be solved, but that will not have a solution of this form. It will have a solution which can be obtained, and again, that would be a nice exercise to work that out. So let's discuss the nature of the solution when this condition is satisfied. We can note from this behavior, or we can simply look at the equation and see that if f e prime is not equal to 0, if this number is a positive number, and we close the second term for now, we would see that this would correspond to a growth equation. The growth rate is this f e dash, and so then z will grow, and so the solution will run further away from the equilibrium solution when this coefficient is positive. And so that would correspond to the equilibrium solution being unstable. Small deviations from equilibrium solutions grow. Now, in presence of the second term, it is possible that deviations from equilibrium solution when f e prime is positive grow, but then they get bounded by the second term and approach a different equilibrium solution. And so that is something that can be found in this solution when the equilibrium solution is unstable, provided certain conditions are met. And this is the case when if the equilibrium solution is stable, then f e prime would be negative, and then this would correspond to a damped solution which will go towards the equilibrium solution. And so let's consider the case where it's unstable and this second term stabilizes it. We can show that in that case we would have this behavior for the solution. As time goes to infinity, it will achieve a new value which is given by this formula. So that's a simple illustration for a first order differential equation where we carried out the truncation to second order. If you want to keep more terms, you will need to do more work to solve the simplified equation. And we're going to be talking about keeping more terms in the series expansion in the context of second order differential equations. But there, the truncation or the series expansion that we're going to be carrying out is not expansion of the nonlinear right-hand side. We will do that for linear equations. So there won't be any Taylor series expansion of the right-hand side, but it will be a series expansion of the dependence of the solution on the independent variable, a power series. And that's something we're going to illustrate more in the context of second order equations. But for first order equations, what we have described should give you a good feeling for the nature of the solutions.